Hey guys, I'm back with another tutorial in the MonoGame series. This one is going to be the first in the 3D tutorial series using MonoGame. So to start, we're going to open up a new Windows OpenGL project. I'm going to call this MonoGame Tutorial 2. Remember, we're going to have to remove the SDL reference. Run. You should see this. Okay, now what are we going to be doing in this tutorial? Well, we're going to render your first geometric primitive. Now, basically, primitives are objects created using triangles. Now, when you play video games nowadays, you see really complex models. Those models are actually a bunch of triangles, thousands and thousands of triangles, because if you put triangles together, you can start making more rounded edges. The more triangles you have, the rounder things get. So to start, we're just going to make a triangle using vertices. Models, meshes, are all made up of what's called a vertex, and essentially all that is just a point in space. So think of around you in the world. Just pick a point, and that's a vertex. A mesh or a primitive is made up of a collection of vertices. Now a triangle has three. Three connected lines make up a triangle. So, and each line connects to a vertex. So to start, you may think, well, how are we going to create vertices? Well, XNA and MonoGame specifically has a couple classes called Vertex Position. Now, see, you have some selections. You have Vertex Position Color, Vertex Position Color Texture, Vertex Position Normal Texture, and Vertex Position Texture. Now, the one we're going to be using is just Vertex Position Color. Basically, we're going to pass in a vertex position and a color that we're going to color that vertice. So we're going to create an array called verts. And we're not going to initialize it yet. We're also going to need two more things. Something called a basic effect. We're going to call it an effect. And a vertex buffer. Call that buffer. Now, what these two things do is the basic effect, essentially what they did with XNA and MonoGame is usually in games there's something called high-level shader language, HLSL, which people write shader files, and then those are run through, and what they do is they take vertice positions and they apply effects to them, like coloring effects and pixels. That's why you have vertex shaders and pixel shaders. Vertex shaders do mathematical operations on vertices, while pixel shaders do pixel precision operations. So that's what this does. Basically, the basic effect is a standard, like the most common shader file was just built into a class. And what this effect class allows us to do is have the standard lighting, Gorad shading, and Phong shading, which I'll explain later in future tutorials, as well as some other interesting effects like diffuse lighting, ambient lighting. So the next thing is the buffer, the vertex buffer. Now, what the vertex buffer does is basically it allows us to take the vertices that we declare and pass them to the graphics device in a more efficient manner. Basically, you pass the buffer to the graphics device, and instead of like it constantly reading the vertices from that array that we make, it reads them from the buffer. It makes everything more efficient. So It's not really that necessary when you have just one triangle being drawn, but once you have a large amount of triangles and primitives, you want to have buffers. So to get started, we're going to go down into the initialize method, and we're going to set up our verts array. So we're going to initialize it with a size of 3, because remember we need 3 vertices. And we're going to create a vertex position color, and what this takes in, as you can see, is it takes in a vector 3 and a color. So new vector 3, 0.0f, 1.0f, 0.0f. So basically what this is saying is this vector 3 is basically just 1 unit up, so straight up on the y direction, and no shifted units on the x or z. And we'll just make this one red, color.red. And I'm just going to copy this and paste it a couple times because we know we need 3. And what we're just going to do is change these. So we're no longer going and shifting up. What we have to do is shift down. So we shift 1 unit down. And what we're going to do is shift over -1 in the right. Now I'll explain how this coordinate system is set up in MonoGame in a second, but just bear with me. So, and then we're going to shift down again and just shift 1 over. So we have basically down 1 in the y, over 1 in the x, and to the right, and then over 1 to the left in the x. And this one I'm going to make blue. This one I'm going to make green. So there we go. We have our vertices declared. So now what we want to do is we want to just create our effect. So we're going to set effect equal to new basic effect. It takes in the graphics device. So we're going to type graphics device, and there's a property conveniently for us. So there we go. So now we have initialized effect. We set up vertices, and finally what we want to do is we want to create our vertex buffer. So buffer is going to be set to new vertex buffer. As you can see, it takes in a couple things. It has 2 overloads basically, this first one and this one. We're going to be using this one, and basically I'll explain it first. So graphics device, of course, you know what that is. We just used it for the basic effect. That's your graphics device. The vertex declaration. Now, each type of vertex structure has a vertex declaration. So that's what you're going to pass in there. Basically it defines how that vertex structure is actually declared, the order and such. Now the vertex count, we know, is 3. There's 3 vertices. And the buffer usage, we're only going to want to write only. So there we go. So, and then we want to set the data, and we want to set into the buffer our vertices that we created. So basically what this does is you create your vertices, your vertice array, initialize all the vertices you need. For a triangle you just need 3. Then you create the buffer using the correct vertex declaration. You determine how many vertices you need, and then you set into the data the vertices array. So there we go. So now we're almost done. So now we want to render this, because you actually want to see it on screen, right? So in order to render, first we have to look at the effect that we have, because there's some things that we need to figure out. Now let's look at what the effect has. Now as you can see, it has some interesting light stuff, fog, but here's where we really want to focus. There's these matrices called projection, view, and world. Now, first I'm going to talk about projection and view. Now, projection, if you think about your head, yourself, and your eyes, when you're looking straight forward, you have a certain range of view. You can see straight ahead for a certain amount of distance, and you can kind of see at an angle up without moving your eyes, and to the side. So you have sort of like 180 degrees every which way. It's a little bit more than that actually, but generally you have that much field of view. That's what the projection matrix is. Basically, since we're working with a 2D viewport, essentially the projection matrix defines that the camera with which we see our world. So when you're playing like a first-person shooter, and you're looking, you have like, the gun, you see, you're looking up and around and everything, you have a specific projection matrix that defines like what you're able to see in the world. So for projection, we set that equal to, if we look at the matrix class, it has a method called create perspective field of view. Now for the field of view angle, the most popular angle, since it's in radians, remember, is pi over 4. Now if you don't know your trig values off the top of your head, pi over 4 is essentially 45 degrees. So that's what most FPS games use, by the way. Now for the aspect ratio, we're going to go back to the graphics device and get the viewport, and the viewport conveniently has a property called aspect ratio, so we can just use that. Now the near plane distance and far plane distance. The near plane distance is the smallest amount, the closest object can possibly be before it gets clipped out. Basically, that's what these near plane and far plane distances are. The near plane is how close to the camera an object can get before it gets erased, like not drawn. And the far plane distance is how far away from the camera before it gets basically clipped out. Because to increase efficiency, you don't want to draw everything in the game unless it's visible. So you have to determine, when something is essentially not visible by the human eye. So we're just going to set these to 0.001 and 1000. Next is the view. Now the view matrix is interesting. The view is basically where the origin of the camera is coming from and then stems from. So basically this is essentially the camera position, where the camera is looking, and what defines up for the camera. So the y-axis, like how that's defined, that's what the view matrix basically takes care of. So with like a first-person camera, your view matrix, because of the rotation, you basically rotate around, and the view matrix changes based on when you rotate up. So it simulates like your head looking up and down. That's the view matrix. But everything you see also changes based on that. And that's what this view matrix does. All the stuff that's being drawn, based on the view matrix right here that the effect is giving, it will essentially shift how the world's being drawn, as long as you have a consistent view matrix. So for this, we're just going to set it to matrix.createLookAt, so where it's looking. Now it wants a camera position, so we're just going to set it to 0, 0, -5. So we're going to shift it back a bit. The camera target, we're going to set to vector3 forward. Now forward just defines a basically 0, 0, 1 in the Z, so straight into the 3D space. And for the up vector, vector3 up, which is just essentially up, like 1 in the y and 0 for x and z. So the next thing is world. Now world, the world matrix defines basically how the object that you're working with should be drawn. Now in our case it's just a triangle, a primitive. But if you have like a 3D model, this world matrix, all the transformations and rotations and scales you do on the world matrix translate to what you like how you see the object and where it's positioned in the actual world. So basically, you scale it in its local axis. So basically, you do all the scales, rotations, everything in its own local axis, and then it gets transformed into the world that you're actually viewing. That way, you don't have to worry about going like, oh, is this object at like 200, 500, negative 300, and then doing like weird rotations using those values and translations. What you do is you translate it based on its local like position. So basically like 1, 0, 1, negative 1, all those. And then it just gets shifted based on where you want it. So what we're going to do for now is just set this to matrix.identity, and that's just the identity matrix, so 1 on the diagonal. So the last thing that we're going to want is there's something called Vertex Color enabled. Now because we're using vertex position colors, we really want the vertex color enabled to be true, because we want to see the colors that we passed in. If that's false, then you won't actually see any colors. And that's all we need basically for the effect. Now to draw, what you need to do is there's something called an effect pass. So we're going to do a for loop for each loop through, and we loop through for each effect pass in effect, current technique, passes. Whoops, I still deleted that. We're going to apply the pass, so that applies basically the effect to the call on the graphics device. And then we're going to call graphics device.draw user primitives. We're going to pass vertex position color. Primitive type is going to be triangle list, I think. Strip would work too. We need to pass in the vertex vertices and the vertex offset, which is 0, and the primitive count, which is 3. Yeah. Oh wait, no, that should be 1, by the way, because that's not the vertex count. That's actually the primitive count. So yeah, since we're only drawing 1 primitive, because each triangle would be a primitive, so you're just passing 1 there. So let's run this, and you should see, there you go, you should see the triangle appear. Now that's pretty cool, right? So what I'm going to show you quick how you can do basically how this world matrix works. So we're going to do some quick things. We're going to create a vector 3 called position, and we're going to create a float called rotation y. Okay, and we're going to go down, and here the initialize, we're going to set our triangle's position. So position is going to be set equal to new vector 3, and we're going to do zeros for all these, and we're going to shift it I don't know, 5 into the world, so it's a little bit farther away from us. And in the update, what we're going to do is we're going to cache something called delta time. And basically what delta time is the times that's elapsed since last frame, and it's used to make it so all animation is smooth and independent of basically the processor speed in varying machines. And that's equal to game time.elapsed game time.total seconds. So always remember that. It's very useful. Just in any game you ever make, always remember delta time. And what we're just going to do is we're going to take rotation Y and just add delta time to it. Plus equals delta time. And we're going to take this matrix.identity and we're going to multiply it by matrix create rotation Y. So what this is going to do is it's going to return a matrix that has in the Y rotation position column and row. It's going to have our rotation Y value, and then we're finally going to multiply by create translation and see how it takes in a position. We're just going to pass in our position. So if we run this, you should see the triangle is shifted back. It's farther away from the camera now, but you can see a strange effect happening. Why does, after it rotates 180, it like disappears? Well, this is because XNA has something called, well, in all 3D graphics, not just XNA and MonoGame, in order to increase efficiency, the graphics device will cull. It's called back face culling. The back side of primitives is never supposed to be seen by the viewer. So what they do is they cull it, they cut it out, and to increase efficiency. Now there's a way to turn this off. If you go up to the initialize in the game 1 constructor and you set graphics device dot rasterizer state equal to rasterizer state dot cull none, what'll happen now is if we run this, you'll notice that it spins and you can see the backside. That's because now it's not culling anything. And this is very significant in that you have to be careful in the order in which you declare the vertices of the triangle, because they have to be declared in counterclockwise fashion. I mean, not counterclockwise, in clockwise fashion. Anything declared counterclockwise is called out. So if you notice the back sides of any primitive, the vertices would be ordered counterclockwise, and that's why the graphics device cuts them out. So to show this, if I get rid of this right here, so now it's actually culling. It's culling clockwise. If we change this negative to a positive and change this positive to a negative, so now we go one up, down to the left, and then down to the right. That's counterclockwise. We won't see anything. But now we do. See how the rotation? So now it's actually drawing the back of it, because the back face is actually in clockwise. So whatever side you want to see without, when you're creating, let's say you're creating a cube, you need to make sure that you're rendering correctly the front faces and the back faces. Otherwise you won't see anything. Basically it'll be like the cube is inverted in itself. So that is about it for this tutorial. I hope you found it educational. In the next tutorial, I'm going to go over how to render geometric primitives such as a cube using an index buffer, which allows you to do things much faster and allows more flexibility. So Thanks for watching, and stay tuned for more.